of you maybe got an email from me about this, but I guess maybe anyway, maybe you probably did. So I am actually giving a talk tomorrow at 11 about what I did on my sabbatical. So some of it I'll talk about disco. I'll also talk about this silly robot programming game that I made, and some of the things they have in common, and some interesting kind of programming techniques that I learned. So it should be fun. It'll be at 11 to 12 in 3:15. I guess that's what it is. Love to have you come if you want. So, all right. So we're going to talk much more about Bézout's theorem today. So remember just the motivation, right, that we had our frog, and it could, make some kind of hops and jumps of different sizes. And the question is, if it repeatedly jumps and hops around, what places can it reach? In other words, if we add or subtract as many copies of the jump and hop values as we want, then what values can we possibly get? And I think in the example that we did, right, we had one was 30 and one was 18, and we kind of convinced ourselves that we could do any multiple of 6, and 6 being the greatest common divisor of 18 and 30. The question is, is that always actually true? And it is. So. Again, a lot of times when there's a theorem name for someone, I go and learn about who that person is, and kind of what the story is. But I don't know anything about Bézout, so if you want to go look up what the story is. So I'll just recopy it here. I think we wrote it last time. But we've got some natural numbers A and B. Then there exist integers S and T. S and T in a set of integers such that SA plus TB equals the GCD of A and B. In other words, you pick any two numbers, it's always possible to add or subtract some number of copies of those numbers to get their GCD. Okay. And it's not obvious why we care about this, but we don't necessarily care about frogs jumping around. But we'll see. I think we'll get to it today. We'll see. There are several important applications of this. This is actually, well, we'll get there. Okay, so I'm going to kind of give a proof sketch. That is, I'm not going to write out every single detail, but I'm going to give enough that hopefully you'll be kind of convinced, and that you could go and fill in the little details yourself if you wanted to. Okay? So here's what we're going to do. So let big S is going to be this set. It's going to be the set of things of the form J times A plus K times B, such that J and K are any integers. Okay. In other words, so again, thinking of A and B, right, are in our example were like the amounts that the frog could hop, and so this is like, look, pick any number of jumps and any number of hops you want, and where do you end up? So basically anywhere. This is the set of all places the frog can possibly end up. Right. So another way to say this is the set of all, they're called linear combinations. So this set is definitely infinite. It's got, because the frog can just keep jumping as far as it wants in either direction, so it's got lots of negative things, lots of positive things, infinitely many. However, because it's a subset of the integers, there has to be some number in there which is the smallest positive number in that set. So if this was like rational numbers, that's not necessarily the case, because you can always keep finding smaller and smaller rational numbers that are positive, right? But if I've got some integers, there's got to be one integer in there that's as small as possible among things in the set that's still positive. And maybe it's 4, and maybe like 1, 2, and 3 don't occur in the set, but 4 is there, so like, okay, 4 is the smallest positive thing. Maybe it's 1, I don't know, but has to be something. So let D be the smallest positive element of S. And our goal is to show that D is in fact equal to the GCD of A and B. Okay. So this is actually, we're actually proving slightly more than what the theorem says. The theorem just says, yeah, you can get the GCD somehow. This is saying, and actually, not only can you get it, that's actually the smallest thing you can possibly get. Like, you can't get anything, well, of course you get negative things, but like the smallest positive thing you can get. So in our frog example, we could get 6, but we convinced ourselves that we couldn't get, anything less than 6. We couldn't get like 3. I mean, that's not, and I guess that wasn't too hard to see, because since 18 and 30 were both multiples of 6, we're always going to have multiples of 6. So we can't get anything between 0 and 6. Okay, and how are we going to do that? Well, the definition of the GCD, you don't have to go back and look, but basically we need to show that, first of all, we need to show that D divides both A and B. And then we also need to show that if anything else divides A and B, then it also divides D. So, to show that D divides A, and we're going to, and D divides B, and we're going to show that if C divides A and C divides B, then C divides D. Okay, how are we going to do those things? Well, the second one is pretty easy, actually. If C divides A and C divides B, well, D is something from this set. So D is of the form something times A plus something times B. And if C divides A and it divides B, then it's going to divide this linear combination of them. Right? If I have some number of copies of A and some number of copies of B, and C divides all of those copies, right, of both of them, then when I add them together, I'm still going to get something that C divides. So this is easy. D is of the form JA plus KB. And if you want to be pedantic about it, right, there were some theorems we proved about properties of the divisibility thing. We said, oh, if C divides A, then C divides J times A, and if C divides these things, then you can add them and it still divides that, right? We proved all those things. So we know that if C divides A and B, then it's going to divide something that looks like this. Okay, so what about this thing, to show that D divides A and D divides B? And this is the part I'm going to leave out some details. But here's how we're going to do it. So we're going to use the division algorithm to say D equals, A QD plus R. So if we divide A by D, we'll get some quotient and remainder. then show that R is an element of S. What does that mean? Well, for R to be an element of S, it means that R is of this form. It's something times A plus something times B. This is the part I'm going to leave out, but you can figure this out. Right? We can just subtract QD from both sides and think about the fact that D was of this form. So Q times something of this form, and then like minus A, or like A minus that. You can kind of rearrange stuff, do a little bit of algebra, and you'll definitely get something of the form, some expression times A plus some expression times B. I'm not going to do the details because it's just algebra basically. All right, I'll just say this, right? R equals A minus QD. So it is of the form KA plus KD. Oh, and I didn't leave myself enough space. But this is not a chalkboard. Ta-da! Right. Okay, but here's the cool part. So, because we use the division algorithm, R is the remainder, right? So it has to be less than D. It's between 0 and D. So it's R is between 0 and D. It's less than D, but it's in that set. But what is D? D, we chose to be the smallest positive thing in that set. So how could R possibly be smaller than it and also in that set? The only possibility is that R is actually 0. It can't be anything positive and smaller than D because D was the smallest thing in the set. So, but R is less than D, and D is the smallest positive element of S, so R equals 0. And this is kind of a sneaky trick that many proofs involving showing that something divides something else works this way, where you say, well, let's try dividing, I want to show that D divides A, so let's just try dividing A by D and see what the remainder is, and then argue why actually the remainder has to be 0. Right? That shows up in, I can think of a couple other kind of proofs of other kind of key theorems that also work that way. Okay, any questions about this? So again, if you like, you can try to fill out more of the details yourself. Also, if you look at the PDF of the lecture notes on the website, there is I have kind of both this sketchy version, and then I also have in the notes a kind of more fully written out version, if you want to look at it. But I thought for class, it's more important just to kind of give the big ideas than to do all the algebra. So, all right. So, but here's the thing about this proof. Right, this theorem says there exist certain integers such that blah, and the proof, we proved that yes, those exist, but if you think about how this proof works, it doesn't really help us find them. Right, it just says, well, S has to have some smallest element. I don't know what it is. I don't know what the J and K are for that smallest element, but there's some smallest element. And then, oh yeah, it turns out that's the thing we want. So it exists. But that doesn't really help us find what those values of S and T actually are to get that smallest element. So this is what people would call a non-constructive proof. That is, it just proves that something exists, but it doesn't really tell you how to find it. Which is better than nothing, right? But it's somewhat unsatisfactory perhaps, because you know, I want to know what S and T actually are. In some cases, you know, there are theorems that people have come up with and proved, and nobody knows how to prove it constructively. Like, it's like we know that this has to exist, but we don't really know how to find it. Fortunately, in this case, we actually do have a good way to find S and T. So I'm going to show you how that works. So, given A and B, how do we find S and T? So, we're going to use something called the extended Euclidean algorithm. And I'm going to kind of present it to you in the way that I like to do it, that I think makes sense to me. I mean, there's other ways to present it, and if you look online and stuff, you'll probably find many different explanations of it that work differently. But this is the way that I learned it when I took discrete math, and it made a lot of sense to me. So here's what we're going to do. So I'm just going to work through an example. And we'll use our friends 60 and 18. So we expect to get 6 as their GCD. But the question is, like, how many copies of A plus how many copies of B will give me 6, actually? So here's what I'm going to do. I'm going to make a table, make a column for S, a column for T, and I'm going to make a column for 60S plus 18T. And then I'm also going to make a column for Q. The Q column is optional. You can kind of do it in your head, but I'm going to do it here. So here's what we do. We always start with the same 2 rows. We start with a row where S is 1 and T is 0, and another row where S is 0 and T is 1. So this, right, we always start with this. And the idea is that this column here, like whatever S and T are, this is going to be 60S plus 18T. Okay, that's what it says. So when S is 1 and T is 0, 60S plus 18T, the 0 cancels the 18, and we just have 1 copy of 60, so this is 60. Right, and of course, other way around, when T is 1 and S is 0, we just get 18. Okay. So we, in fact, we're always going to, these 2 things, we're always going to start out with whatever our 2 numbers are, A and B. Those will be in those first 2 rows. So I'm going to, basically what we're going to end up doing is that this column, we're going to run the Euclidean algorithm. And you'll see how that works in a second. But basically, if we ignore the rest of the table and we just look at this column, it's just going to be like the numbers you would get when you run the Euclidean algorithm. But we're also going to keep track of some stuff over here that at the end we're going to end up with the values of S and T that we want. Okay? So how does the Euclidean algorithm work? Well, we would say, all right, 60, 18, like it's not 0, so I'm going to basically, if this is my A and this is my B, the next step I'm going to have, this is going to be my new A, and then I'm going to do like A mod B, and get the remainder, and that would be my new value of B. So 60 mod 18, I don't know, I think it's actually 6. I think 3 times 18 is 54, and then we have 6 left over, right? So the important point here is that instead of just thinking about mod, I really do want to think about how many 18s did I have to subtract from 60 to get the remainder. And that's what's going to go in the Q column. So this is 3, and this is 60 div 18. Right, so I look at these 2 rows and I say, well, 60 divided by 18, 18 fits 3 times. And I mean, I guess I could, well, I'm not going to make another column for the remainder because I'm going to put the remainder below. I'm going to put the remainder here. This is 60 mod 18. Right, because when I do the Euclidean algorithm, I start out with 60 and 18, and the next step, I'm going to have 18 and 6. Right, because my A, like my old B becomes my new A, and then the remainder is my new B. So every time I do a step, I'm going to like move down a row. Okay, what am I going to put here? So here's the interesting trick. Because each row kind of corresponds to an equation saying, 60 times this plus 18 times this equals this, right? You can add and subtract equations. If I have two equations that are true and I kind of add both sides of them together, I get another equation that's also true. Also, if I have an equation and I multiply both sides by the same thing, it's still a true equation, right? So I say, well, look, to get 6, I subtracted 3 times 18 from 60. So if I subtract 3 times this from this, and also subtract 3 times this from this, I'm going to get another true equation down here. Okay? Because I want to know what S and T, what are S and T such that 60 times S plus 18 times T will be equal to 6. So I'm going to say, all right, 3 was the quotient, so I'm going to subtract 3 times the second row from the first row. Now, you have to be really careful with your negatives and positives here. It's very easy to get confused because you're like subtracting a negative, and but you just have to like be careful. So in this case, 1 minus 3 times 0 is just 1. So actually, I'm already in the middle of the row. So we're going to subtract. Subtract 3 times row B from row A. Let's get this. And 0 minus 3 times 1 will be negative 3. Okay, and we can double check at this step, right? It should always be, each row should always kind of make this valid. So 60 times S plus 18 times T should be equal to this, which it is, right? So 1 times 60, 60, plus 18 times negative 3, that's negative 54. So 60 minus 54 is 6. And if I did one more step, right, I would say, well, 6 goes into 18 3 times, and the remainder is 0. At this point, though, I can stop, because when I get 0 here, that means that this actually was the GCD. Right? The thing right before 0 is always the GCD. And so that means that this S and T are the S and T that I want. So, right, so this tells me that the GCD of 60 and 18 equals 6, and also that 1 times 60 minus 3 times 18 is how I get that GCD. Okay, let's do one more example. Any questions at this point? This is one of those things where, I'm trying to explain it in such a way that I hope that you can kind of understand why we're doing this and like why it works. But of course, if you also just want to memorize the steps, you can just memorize the steps and you can do it successfully without really understanding why it works. But as with most things, if you understand why it works, it'll make it easier to do it. It'll make it easier to remember what the steps are that you're supposed to do, and you'll be less likely to, to mess up, to do a wrong step. So let's do one more example. Let's make a new page. Example. What do we have here? Let's do A equals 39 and B equals 16. Now, we can look at that and say, yeah, those clearly don't share any common factors. So their greatest common divisor is going to be 1. So we expect to get 1. But the question is, how many copies of A plus how many copies of B do I have to add to get 1? Right? That's what we're trying to find out. So let's make our table. Here's my S, here's my T, here's 39S plus 16T. Here's my quotient Q. So I'll start with 1, 0, and this is 39, 0, 1, 16. Okay. So how many times does 16 fit into 39? 2 times, yes. Good. So my quotient is 2, and then, whoops. What? Can't zoom back in. Oh. It's in presentation mode, whatever that means. Presentation mode is the mode where it's too small to present anything. Okay, and what's the remainder if I do 39 mod 16? Like if I subtract 2 copies of 16. So 16 times 2 is 32, so I get 7 left over, right? Yeah. So the 7 goes here. Okay, and then I think, all right, to get the 7, I subtracted 2 copies of 16 from 39, so I have to do the same thing in each of those places. So I'm going to subtract, 1 minus 2 times this, and 0 minus 2 times this. So here, 1 minus 2 times 0 is 1, and 0 minus 2 times 1 is negative 2. Right. And if I want, I can always check. I mean, at this point, it's pretty easy to check, because it's just like, well, yeah, 39, 1 times 39 plus negative 2 times 16, yeah, that's 39 minus 32, which is 7. That makes sense. All right, let's do the next step. So, 16 divided by 7, quotient and remainder. The quotient is 2, yeah. Actually, the remainder is 2 also, right? Okay, so I'm going to do the same thing. I'm subtracting 2 copies of, here I subtracted 2 copies of 7 from 16. So I'm going to subtract 2 times these things from these things. So 0 minus 2 times 1 is negative 2. And here's where we have to be careful with our signs. 1 minus 2 times negative 2. Right, so 2 times negative 2 is negative 4. 1 minus negative 4 is the same as 1 plus 4, which is 5. Right, and if you're not sure, right, again, we can always double check each row. So we should have that negative 2 times 39 plus 5 times 16 should be 2. And does that make sense? Well, negative 2 times 39 is negative 78. And 5 times 16 is 80. So that does indeed give 2. And you just put it on a calculator, right? Or a disco. And check that that's. Okay, 7 divided by 2 gives a quotient of 3 and a remainder of 1. And so now we're going to be subtracting 3 times this row from this row. So 1 minus 3 times negative 2. 1 minus negative 6, that's 7. And negative 2 minus 3 times 5, negative 2 minus 15, that's a negative 17. And, I mean, if I kept going one more step, I would, of course, get 0 here. I mean, as soon as I get 1, I know that's the GCD. I can't get anything smaller than that. So, but just, just to be complete, I'll lose it. But that means, right, the part I care about is this. Right, so that tells me GCD of 39 and 16. minus 17 times 16 equals 1. And we could double check that on a calculator. It should be correct. I definitely would not want to like try, different combinations of 39 and 16 until I happen to stumble upon, adding 7 of 39 and subtracting 17 like that. That's crazy, right? But not hard to calculate this way. And of course, this takes the same number of steps as the Euclidean algorithm, so it's going to be very efficient, even for very big numbers. It's not going to take that many steps. Okay, any questions? Okay, so why do we care? We don't care about frogs. I mean, well, frogs are nice, but why is this an interesting and important theorem? So there's one super important application that I'm going to tell you about right now. There are others, but this is the biggest one. Theorem. This is a theorem about modular inverses. Right, so remember how if we have like a modular equivalence, we can add to both sides, we can subtract, we can multiply, but we can't divide. Right, dividing is forbidden. Basically, this theorem is going to tell us sometimes you can, and like exactly when it's possible to divide, and when it's not allowed. Okay, so let A be an integer, and M is a positive integer. If GCD of A and M equals 1, right, I'll say that is A and M share no common factors. Then there exists an integer b such that a times b is equivalent modulo m to 1. And we say that b is the modular inverse of A mod M. So, what does this say? So let's think about like, what does division even mean? Like if we're just thinking about like, dividing with fractions and stuff, just rational numbers. If I say I want to divide by 2, what does that mean? Well, dividing by 2 is the thing that undoes multiplying by 2, right? It's the opposite of multiplying by 2, right? If I multiply something by 2 and then I divide by 2, I get back to where I started. So another way to say this is dividing by 2 is the same as multiplying by something that would undo multiplying by 2, and that thing is a half, right? And you all probably learned this in 5th grade or whatever, that dividing by 2 is the same as multiplying by 1/2, right? So 1/2 is the inverse of 2, like with respect to multiplication. When I multiply 2 times a half, I get 1. They cancel out. And if we're talking about rational numbers, right, then every number other than 0 has an inverse. 17, the inverse is 1/17. 2/3, the inverse is 3/2. There's always another number that I can multiply by to get 1. And that's what this is saying. This is saying, look, if you've got a number, if we're talking about kind of the world, modulo m, we can't say, like a half, but there could be some other number that kind of acts like a half or whatever, in the sense that if we multiply by that other number, we won't literally get 1, but up to equivalence modulo m, we'll get something that is equivalent to 1. Okay, and this theorem says, yeah, that works exactly if A and M don't have any factors in common. Okay, so if A is 2 and M is 4, then you're out of luck. There's nothing you can multiply by to get 1, because it's always going to be even, basically. But if A is 2 and M is 5, then yes, there's some other number that you can multiply 2 by to get something that's equivalent to 1, modulo 5. So I'm going to do a proof. The proof is actually super short now that we have Bézout's theorem. Well, A and M have a GCD of 1. So Bézout's theorem tells us that I can add some number of copies of A and some number of copies of M to get 1. So by Bézout's theorem, there exist S and T such that SA plus TM equals 1, their GCD. Right? Then that means SA plus TM is equivalent modulo M to, well, I could just say 1 is equivalent modulo M to SA plus TM, because they're actually equal. But look, T times M, that's a multiple of M. So that is equivalent modulo M to 0. It has a remainder of 0 divided by M. So that's just SA. Well, look at that. Here's something times A that's equivalent to 1. So S actually is the modular inverse of A. So S is the modular inverse of A. Okay, and we'll do an example. I will mention this theorem, it's actually an if and only if. I didn't prove the other direction, but if you like, you can think about how you would show the other direction. That this says that if the GCD is 1, then A has a modular inverse. The other direction would say, if A has a modular inverse, if there's something you can multiply by to get 1, then actually that means that the GCD of A and M has to be 1. I'll let you think about how you do that. So, example. Solve for x. 3x is equivalent modulo 7 to 5. So previously, we would have, we've looked at equations like this before, but we would have been stuck at this point before because we don't just have x is equivalent to something, and we wouldn't know, like, we didn't think we were allowed to divide by 3. And we can't literally divide by 3, because saying 5/3 doesn't make any sense. We're just talking about integers. But because 3 and 7 don't share any common factors, this tells me that there's something I can multiply both sides by that will cancel out the 3. Right? It's kind of like dividing by 3. Okay, so since 3 and 7 share no common factors, 3 has an inverse on 7. And if we multiply both sides by the inverse, it will cancel the 3. Or in other words, right, when we multiply by that inverse times 3 is equivalent to 1. And so we can just replace it by 1. So we'll just get x. So what is the inverse of 3? Well, we can use the extended Euclidean algorithm. So we can compute the inverse of 3 using the extended Euclidean algorithm. Now, I mean, in this particular case, it's actually not too hard to just like try a few numbers and figure out and like find one that when you multiply it by 3, you get something that's one more than a multiple of 7. But I'm going to do the actual algorithm just to show how we would do it in the general case. So the numbers that I have, so here's my S and T, and this is going to be like, we'll say 7S plus 3T, because right, it's in particular the fact that 3 and 7 have a GCD of 1, and when I find the S and T, I guess in this case T, which is the thing we're multiplying by 3, that's going to be the inverse of 3. So we'll say 1, 0, 7, 0, 1, 3. Let's see, 3 goes into 7 twice and leaves a remainder of 1. So when I subtract 2 of this, so 1 minus 2 times 0 is 1, 0 minus 2 times 1 is negative 2. Well, and I'm done. Right, this is the GCD, so. And again, I already knew I was going to get 1 here, so that's not interesting to me. The really interesting thing to me is T, right? Because that thing times the 3 was giving us something that's equivalent to 1. That's what we want. So the answer is minus 2, or we could also say 5, because that's equivalent modulo 7. But we use minus 2. So that means we multiply both sides by minus 2. We get, well, we know it's going to cancel the 3, right? Well, we can, let's check, actually, let's double check. Minus 2 times 3 is minus 6, which is equivalent modulo 7 to 1. So that does work. Or if we had thought of this as 5 instead of minus 2, 5 times 3 is 15, and 15 again, equivalent to 1. It's 1 more than a multiple of 7. So if we multiply both sides by negative 2, we get negative 2 times 3x is equivalent modulo 7 to negative 2 times 5. And then we know that these are going to cancel out. So we'll just get x is equivalent modulo 7 to negative 10. And we could rewrite that if we want to say that's equivalent to, I guess it's equivalent to 4. And if I add 7 twice. So that would be a solution. X is equivalent to 4. Questions? I guess we could also, it's a good idea to go back and check, right? If x is 4, if I stick that back in here, I'll get 12. And yes, 12 is equivalent to 5, modulo 7. So that seems to work. Let's do one more example. Solve for x. 3x equivalent modulo 9 to 5 minus x. What should I do first? Yeah, we definitely want to combine all the x's first. So if I kind of like didn't see this, I just said, oh, 3x, so let's like find the inverse of 3 and multiply both sides by that. Well, number one, that wouldn't really help because I still have an x over here. But also, 3 doesn't have an inverse modulo 9, right? Because 3 and 9 share a common factor. They're both divisible by 3. So there isn't actually anything I can multiply by to get rid of the 3. But if I add x to both sides, so So that implies 4x equivalent modulo 9 to 5. Okay, and now 4 and 9 do not share any common factors. So now I can find an inverse of 4. So let's see, find inverse of 4 modulo 9 s plus 4 let's see, so this 2 is the remainder of 1. I'm not taking great examples, but there's only one step to do this. So again, subtracting 2 times this, so this leaves 1, 0 minus 2 times 1 is minus 2. And so, I guess it's minus 2 again. Does that make sense? So minus 2 times 4 is minus 8, which is 1 more than multiple of 9. So that does make sense. So multiply both sides by minus 2. Actually, it's great. And I'm just going to get x is equivalent modulo 9 to negative 10, which is equivalent to minus 1, or I could say it's equivalent to 8. All right, I kind of like minus 1 better. You don't have to, write it in the form of something that's between 0 and 9. So yeah, a nice way to write this one would be x is equivalent modulo 9 to 1, and minus 1. Again, we can check. So 3 times minus 1 is minus 3. 5 minus negative 1 is 6. And negative 3 and 6 are equivalent modulo 9. Because they differ by 9. So check. Okay. Questions? All right. So on Friday, we're going to finish up this kind of modular equivalent stuff. In particular, there's one more really cool theorem we're going to talk about that will let us solve like systems of multiple modular equivalents.